not forget to start the record here. Okay. So for those who just joined, we have still a technical issue with the projector, but somebody is coming to fix that. But we can get started in the meantime. I can share my screen with you folks. And, all right. Okay. All right. So picking up from last lecture, we talked about the software-defined internet routing, and we discussed, why it makes sense to start from the IXP, and we talked about the challenges in building a software-defined internet exchange that is scalable and flexible. The key ideas that we discussed was that SDX, to enable SDX, we require something called virtual switch abstraction, where we provide an abstraction to each and every participant at the exchange point, as if they have access to a virtual switch, which is as real as it can be, and they can express their SDN policies without worrying about what the other participants' policies are. And then we talked about scalability, and we discussed different techniques for addressing the scalability challenge. And we also discussed that the scalability problems arise because we are trying to ensure compliance with Border Gateway Protocol, which everybody else outside the exchange points are using, right? So in today's lecture, we are going to follow up on what we learned, but now shifting our focus a bit inward, right? So we talked about inter-domain routing, which is like networking between different domains or different networks. Now we're going to talk about the networking within a particular administrative domain or AS, and we'll focus a bit more on the content providers, which are relatively massive and require some specific networking input. Okay, so we'll have some small distraction in the class because we are trying to get the projector right, and those of you who are over Zoom, you'll see what I'm sharing, but I think those of us who are here will soon see the screen projected. It's a dream. All right. Hey, are you here to help? Yeah.
Yeah.
All right. Thank you. How do you want to do?
Just try and see what's wrong.
Okay. So I shared some notes about different updates that we have for the course. Any questions so far for quiz, midterm, lectures? No. I'm guessing everybody was able to submit the assignment on Friday. Yeah. Okay. Yeah, I think we should be giving back the results for the assignment maybe by tomorrow or Wednesday. So that should give you feedback on how well you did. Yeah.
How are we going to see the results?
That's a good question. I think so Gotcha Space is the standard approach. I think maybe we can do that, but I really don't like to use it. But maybe we can do that. Yeah.
I think most of the CS department uses Gradescope.
Gradescope, yeah.
You just submit the code and the
Okay, we can try that as well. But I think until now we were using Gotcha Space for sharing the results. Okay. So projector does work, huh?
Projector does work. Seems to be a problem with the connection here. You have another port you can try?
Yeah, we have 4 ports. Yeah. I tried these two. Maybe we can try that one.
So another adapter. Do you know if this adapter works for sure?
Well, I just bought it, so this is the first time I'm trying it.
Must be a problem with HDMI cable.
Okay, I think like we can resolve that offline. I think I can,
Yeah, I'll put in a help ticket for that, but there's nothing really I can do right now about it because
no problem. I understand.
I
All right, thank you.
possible to try it doing it off the election.
No, I won't use Windows. All right, thank you. Thanks for the help. All right, so I guess we're gonna fall back to our usual. Sorry about that. Hopefully we'll find a solution one day. This project is gonna work. All right, so let's put that board to some use. All right, so as I was saying that like in the last lecture, we were focusing more on interdomain routing. And now we're going to talk about the wide area network, that is the network within a particular AS. Wide area network doesn't really make sense for some of these ASs such as UCSP, right? So UCSP is just one location, so it's just one area, right? But think about the content providers like Google and Netflix and Amazon. So they are geographically distributed across different locations. So the concept of wide area network makes sense that like where they're trying to offer communication or network connectivity between different sites that belong to the same organization, right? So we're going to talk about wide area network in general, and then we'll focus a bit more on the specific wide area network that Google built using software-defined networking. And we'll try to connect, so far we have learned all these basic building blocks for software-defined networking. So then we are just going to analyze and think about how that type of network is going to be built and like how software-defined networking was useful, instrumental in making or supporting these new set of requirements that the Google had a couple of years back. Okay. So let's start with the discussion on how do we access content in the first place. Any suggestions on how do we access content? So you are sitting on your laptop here at UCSB, and this is internet, and maybe this is Google's network. How do you access some content sitting here, right? Say maybe YouTube or just Google. Yeah. Sorry, what?
You make a HTTP request.
Yeah.
It'll be packaged in an IP frame. It would be sent to your nearest router, which would be inside that first AS.
Right.
And use BGP to discover the links to Google.
Right. Is BGP running on your laptop? No. Okay. Maybe we should have another layer of abstraction here. That this is UCSB, right? And within UCSB, you're sitting here. UCSB has a border router, right? And that border router is talking to a border router of another AS. Maybe let's not call this internet, right? So you have different ASs. Oh, that's some massive stuff. You have different ASs, and this is a provider of UCSB. This is border router, right? Both of them are border router of different ASs. They will establish a BGP session with each other, right? And that's how they're going to exchange routes with each other. So first time when you're sending any type of request, the most important thing is the DNS request, right? Because you will say google.com, but what does google.com mean, right? Like you cannot establish any session transport layer connection with any server without knowing what is the IP address, right? So the first thing that you really need to know is that what is the IP address of a particular session, right? And now when I say that this is Google, now Google we know is geographically distributed, right? So Google might have, some sites at LA, right? Well, maybe let's call this SF, right? So SF, and then we have something at LA, right? So now when you're sending this, request www.google.com, it has to resolve to an IP address, right? So Google has to decide which IP address it responds with, right? You might have a different IP address for the router sitting at San Francisco and different for the LA, right? So given that you are closer to LA, Google might resolve that to an IP address that is sitting here, right? Now, questions: how will Google know you are close to LA?
Or IP addresses like statically fixed to geographic location.
Sometimes, like, they're definitely fixed to AS, right? So everybody knows what is the, like, so when a request is coming from your machine here, people outside will know it's coming from UCSB, right? If UCSB is just one location, it's very easy decision for them. But there are these ASs that are spread across multiple continents, then it gets really tricky. Yeah.
What about travel time?
How about what?
Travel time, like calculate the time.
Okay.
Between the IP address.
Right. So yes, I think you can definitely measure the time and maybe send some probe packets to figure out how far this IP address is. You can do a lot of things, right? But then it's just a DNS request, right? So when a DNS request is going in, the information is that, hey, like, what is the IP address of the entity that is sending this request, and it will have what is the domain it is requesting, right? Beyond that, default DNS does not have any additional information. But if you are like if you're using a DNS server that is like using extended DNS version, then you can add some meta information about the client, and that's what Google used a lot to map a particular IP address to a location and then make these type of optimal decisions. The reason we are discussing this is that this is a very active area of research. It has been for a very long period of time. Like extended DNS is something which was out there as an optimization to solve these type of problems, but then there is this whole world of how do you figure out the right mapping for a particular IP address, like client IP address, to your site in a wide area network, right? So this is a complete area, like complete different topic of research. But one thing that a lot of organizations do beyond DNS is that they advertise the same prefix through two different locations, right? So if the prefix that we're talking about, our IP address is, say 140.250.something/16, right? So this is the prefix that we're talking about. It can choose to advertise the same prefix from San Francisco and LA, right? So the intuition here is that if we do this type of thing, then whoever is network wise close by, they should receive it, both these advertisements, and they will the UCSB will receive a path from SF, will receive a path from LA, and then it can choose based on the number of network hops. It can choose the LA most likely. It is not possible, right? It is possible that this is a bit circuitous path, and this is something. Oh, sorry, this is a bit circuitous path, and this is a bit straightforward, like less AS hop. These are all possibilities out there, right? So bottom line, the mechanisms, there are multiple mechanisms in play to figure out that how exactly your router here is going to figure out which IP address it has to establish the TCP connection with, right? And then it will send the HTTP request. First, it has to establish the TCP connection, or like the quick session, which is a different type of transport, and then it will start sending the HTTP request, and the connection will start, right? So far, clear? Okay. Any questions? All right. So now the question is that, okay, the request is coming at this site. Is this the site that is providing us all the content? Is this the router which has all the content? No, right? Router is just a router, right? It's a networking device. So where is it fetching the content from? Server, right? So we need a server. So this is a site where Google has decided to put some routers, but the reason it has decided to put a router here is that it probably has some type of compute servers out there as well, right? So let's think of this as some set of compute servers, right? Now the request is basically processed by the server here, right? Like because whenever we are talking about a connection, then we are talking about an application or like transport layer connection where we have to have an end host, right? So the end host is sitting here. Okay. So this is called front end, right? Google can choose to host all the content on all these front ends, but then it gets very tricky because, like for every location where they're trying to put a router to get as close as possible to the users, they have to put all their content there, right? That's not very feasible thing to do, right? So what they do is that they set up some like massive locations where they're going to establish really large data centers, right? Where they're hosting all the content, doing all the compute. So you can think of those as, sites. You can think of them as backends. You can think of them like massive data centers, like massive data centers out there, right? So the user, as a user, you are getting connected to a front end. We also call it as POP or point of presence, right? So your connection is here, and then the POP or the server sitting here is then figuring out that, okay, what is your actual request, right? And then it is fetching the content from one of these sites, depending on what type of content you are using, right? So maybe it has a lot of things related to Gmail on this data center, a lot of things related to YouTube on here, or maybe all of those content is spread across all these data centers and just figuring out where exactly the content is, right? So this is the basic premise that we have for fetching content, right? And you can think of that like, we were discussing this terminology in the last lecture as well. You can think of this as the eyeball, right? And this as the content, right? So we have all the content here. We are talking about content providers. And the network that is sitting in between, you can think of that as a transit provider, right? So this is the one that is providing transit services to UCSB and to Google to this user. Okay, so the terminologies are clear. Okay, now let's have a bit more internalized view here. Right, this is the front end. We have sites here, sites here, sites here, sites here. Okay, and maybe you can think of them as like multiple front ends at the periphery of the network, right? So before we move into this internal structure, quickly give me an intuition that why does it make sense to have these points of presence of front end as close as possible to the users, right? Why can't we just have all those servers, like all the user requests coming directly to the data center here? Why do we have any type of point of presence outside here? Any suggestions? Like why do you think it is useful to have these servers that are handling your first request or initial request as close as possible to the user? Yes. Yeah, caching. But how does that help?
So like if you don't need to like update data from the servers, you can just send what's already loaded on, or not from the data center. You just send whatever's already loaded on the server.
Okay.
So it's like faster.
It's faster, yes. I mean, like, having it closer to the user basically reduces the latency that each of those users are having. And when we think about latency, like this is a bit more refresher of 176A discussion, but like, latency and bandwidth are two things that determine, how efficient your network connections are going to be. So if your latencies are high, then it will take longer for you to get the response back. And then, like the net quality of connection is going to be degraded if the feedback between two endpoints is slow. If there are packet drops, then it's going to take long time for TCP to converge and operate in optimal state. Yeah.
So the first request, your travel time is still essential for the user to the backend.
Well, so if the content that you're fetching is not cached at the front end, right? So the point of presence, as I said, like they have some servers, they have some storage that they can cache the local requests. And if there are popular requests, right? So google.com response or something, then that's something that can be that is a small content that can be cached locally, right? So that definitely helps by reducing the amount of requests that have to go back, right?
Just to be clear, the POP's locality to the user only matters for subsequent requests, for CAPTCH requests.
Yeah. So that's a good question, right? So this is a bit more fundamental in the sense that rather than, yes, it is going all the way back, but it is splitting the TCP connection, right? So there is somebody sitting in the middle that is splitting the TCP connection. The connection between the user and Google is on a short RTT1 connection. And then it is relying on Google's infrastructure to connect the front end to the back end of these servers, right? Now, why is that meaningful? Why is that useful? Okay, yeah, that's a reasonable answer. What else? Why do you think this type of architecture is meaningful? What purpose does it solve? Okay, let me give you some context here. That when we think of internet, when we think of public internet, right, there is a huge amount of diversity and heterogeneity that we have, right? So maybe when you're connecting from UCSP, you have good connections, but if you're connected to some other ISPs, there are challenges, right? And if you are using some transit providers that are that are congested at times, then your requests are going to get affected and stuff. So what Google wants to do is to make sure that majority of the network journey of packets between you and their content is on Google's network, right? So the closer they are getting to you, they are ensuring the quality of they basically control the quality of connection, right? Like they have this dedicated infrastructure that they have invested in. They are and this is just an argument, right? I'm not saying that this is always true, but this is their argument that they can control how they route the traffic, manage the traffic, handle the packets. And if you are a user who's on a lossy link, which is on your Wi-Fi network, or you're using a cable service, right? So cable-based ISP, think of Comcast and others. So when there is some type of congestion going on there will be some packet drops happening every now and then, right? When these packet drops are happening, and if the round trip time is really high, then it will take long for TCP to converge, right? Because TCP is a feedback, this is all refresher for 176A, right? So TCP is feedback-based approach, right? So it is looking for feedback that I sent you a packet, did you receive it? If you receive it, then I'm going to increase the rate at which I'm sending the packets, right? So this is the fundamental manner in which TCP operates. If the delay for the feedback is greater, if for you're sitting here and this is somewhere in maybe New Jersey, right? So that's a lot of round trip time that we have. If this is the delay that you have in a connection to get the feedback about the link's quality or some packets getting dropped, then your connection is going to be degraded because TCP is going to suffer a lot, right? But if you have shunted that by sending this request only to LA, right? So that's 15 milliseconds compared to maybe 50 plus milliseconds out there. So if you reduce that time, right? So you're able to handle those losses more effectively. And that's the reason why Google is trying to get as close as possible to you, so that they can handle this uncertainty or the heterogeneity in the network conditions, and they can ensure this high quality connectivity between the front ends and the back ends within their own network. Okay. So now that we understand why we need, or why Google or Amazon or Microsoft needs this type of architecture, now the question is, how are they going to make or to provide the connectivity between them, and how can they guarantee that this is high quality, they have better control over the packets that are within their network, right? So first thing is that there are two types of wide area network that we're talking about. One type of wide area network is the network that is providing connectivity between the front ends and these back-end data centers, right? So these are massive data centers, they have to be connected to the front ends. So how exactly they should be connected? That is type 1, or one type of wide area network. The other type of wide area network is how these data centers should be connected with each other, right? So when we think, when we take an example of Google, so this connection between front ends and the back ends is called B2 network. And the other type of network which is connecting all these data centers with each other is called B4. Is that clear? Okay. All right. So I think this should give you some decent context of what we are going to cover in today's lecture, that why do we have, like, what is a wide area network? What are front ends? What are back ends? What type of different wide area networks do exist in a network? Okay, so some of you can already see my slides on Zoom. So I think I'm going to skip some of these initial slides because it's going to talk about what I just discussed on the Blackboard here. But any questions so far? Because this is critical to our next set of discussion. Anything that is confusing here? So B4, as I said, is the network that is interconnecting the data centers. And B2 is the one that is connecting the data centers and the POPs, right? Or POPs, you can front end POPs at the same thing. Okay, so now let's move on to the second phase of discussion today, is that how are these wide area networks connected with each other? What is the routing protocol that should be used to connect these wide area networks? Any suggestions? Maybe I should go one slide back, yeah. So you remember what the discussion that we had for multi-tenant data centers? What was the approach in multi-tenant data centers? What was the guiding principle that we had in multi-tenant data center? Logical data paths, yes. And how were one server connected to the other? Do we remember the concept of tunnels? Right, so basically the logical data path was applied on the server using the virtual switch, right? And once the logical data path was applied, it was clear where this packet has to go. And based on that, it was slapping a header, tunnel header on the top of the packet and sending it to the tunnel, right? And when the packet is in the wire, all it knows is that what is the next hop IP address where it should go. And the routing for those, the forwarding decision that the intermediate routers had to make was very straightforward. They were just looking at the IP of the physical server where it has to go, and that was how the multi-tenant data centers were working. Do you folks remember that? Yeah. Okay. So, in context of the wide area network, can we apply something similar? Right. So, all the programmability, flexibility that we want to apply or we want to support, that can be applied within the data center, right? And when the packet is leaving this data center site to the other data center site, we can just tunnel, put a header on it, encapsulate the packet, put a header of okay, which is the next site it is supposed to go, and then use the existing set of protocols to make sure that the traffic goes there. Is that making sense? Okay. So MPLS was the protocol that was used for sending traffic, from one location to the other, right? So from one data center to the other, MPLS was the protocol that was used, by Google or by most of the enterprises back then. How MPLS works is that MPLS is multi-protocol label something switching, and the key idea is very similar to the tunnels that we were looking at from the multi-tenant data center perspective, that it is slapping a header, it is putting a new set of headers at the top of the packet, and there it just specifies that, okay, now this is an MPLS packet, all you need to know is the next hop IP address where it is supposed to go. And then it uses the OSPF, which you folks remember is the shortest distance routing protocol in place. And that's how it is going from one location to the other, right? So these are this representation might look a bit simple, but think about that. This is somewhere in New York. This is somewhere in Europe, right? So these are really distant locations that we are talking about, and we have a network of intermediate routers that are responsible for carrying traffic from one location to the other, right? So at the edge here, the approach was that you put you make some decisions about internally. You can, in a data center, you can apply whatever you want to do, but at the end of the day, when you have to take the traffic from one data center to the other, then you have to slap a header and say okay, now it has to go to site 1, from site 3, and then at site 1, it will do the same set of process that we observed was the case for the multi-tenant data centers, that when the server was receiving, then at the server, the virtual switch was looking at the packet and then, like removing these specific headers and then deciding that, okay, what specific virtual machine within that physical server the traffic has to go, right? So the MPLS works very similarly, but it is a very standard protocol. It's not software, like it's not software defined networking per se. It's just one protocol that supports encapsulation and enables flexible routing across different type of sites, right? So it's like you can slap MPLS, whatever protocols you have before that, you can just ignore all of that, and these routers that are sitting in the middle can be very simple. They can just look at the MPLS header fields and then make decisions about where exactly the packet has to go, right? So this is how MPLS was working, and everybody was to some extent happy with things as they were. But few things started changing around the time when these ideas came into fruition, right? So the biggest trend that was worrying. Oh, you have issues, yeah.
I don't think the slides are changing.
Oh, really? Okay. So why? Okay, let's see. Thanks for letting me know. Okay. So can you see the slides now? Do you see the transitions? Okay. So I think you didn't miss much because I was putting most of the details on the Blackboard here. But quick recall, we are talking about the wide area network. The B4 is the network which is connecting the data centers, and B2 is the network that is connecting the front ends of the POPs to the data centers, right? And B2 and B4 are very Google specific terms, but this is how fundamentally the design of wide area network is decoupled at each of these organizations. So Google has a different name, B2, B4. Microsoft might have a different name, and Amazon might have a different name, right? But in principle, these are all the same concepts. And I was talking about MPLS-based wide area networks, where at the ingress, which is so if the traffic has to go from site 3 to site 1, so this is the ingress. At the ingress, we basically encapsulate the MPLS headers and send it to, say, site 1. And the routers that are sitting in the middle, all they need to do is just run OSPF and figure out how exactly the traffic is going to reach to site 1, right? Now there can be multiple, links that are connecting site 3 to site 1. So you can, you can create these tunnels, and then you can map flows into those tunnels. And the traffic engineering will be that, okay, what set of flows or what set of packets should go to which tunnel, right? So these are the simple things that each of them were providing. And the MPLS, basically from the forwarding perspective, what MPLS is ensuring is that you don't have to worry about the routing paths per se, right? So all you have to say, okay, from site 3 to site 2, right? The routing paths in the middle can be anything. MPLS is not bothered by that, right? From MPLS perspective, all you have to do is to say that which flow should be mapped to which tunnel, which is the connection between 3 to 2, and then or 3 to 1, and then just apply that forwarding. Yeah.
What's new about MPLS versus just regular routing? I mean, if we're just going from one data center to the other, couldn't we just use?
I think so. Basically, what's unique or what's new? There's nothing much new. I think MPLS is just simplification of the routing protocols, and that is the what it enabled additionally was that it enabled some flexibility in terms of what sort of headers you can push on top of it, right? So what I presented is a bit oversimplification of MPLS, but technically you can also support source routing with MPLS. So what does source routing mean? Source routing means that at the ingress itself, you can specify the specific routing or the precise routing path that the packet has to take, right? And you can basically encode that information into the packet's header and slap that packet header into MPLS. And then the intermediate routers are programmed to, take those or process that packet headers one by one, read it and then discard the hop information at that layer, then slap a new header and then keep forwarding, right? But so there is a value that MPLS adds on top of it, but in context of this discussion, it's not as important of the source routing was still in very nascent stage at that time, and in the context of where we are talking about. But it was basically a tool that the network operators were using for basic traffic engineering, that it just provided a simplified abstraction of the network for them. So that was a version of software-defined networking for the network operators at that time, right? And everything, this was a very stable model. This persisted for 5-10 years. This became a very standard practice that all the network operators were relying on. But the challenge is, specifically when we talk about all these big cloud or content providers, it was very evident that this is something which is not a very sustainable model, right? Now, let's try to understand why that is the case, okay? So what you're looking at in these slides right now is the graph of the growth requirements that the networks had over time, right? So basically the x-axis is time, and we're looking at some graph for around 2 years worth of time. And the y-axis here is basically the amount of data that is exchanged between these data center locations, right? So inter-data center traffic over time is what we're looking at. And the trends were alarming for the network operators. If I'm a network operator, Google, I'll be worried that, if I believe this trend, then very soon I'll be requiring 3 times, 4 times, 10 times the network capacity that I have right now. And then they started questioning that what should be the model of growth for us, right? Should we be, buying more network devices so that, we can just keep up with this increasing requirement or demand that we have? Or do we need to do anything better, right? And that basically leads to this discussion about, is MPLS intrinsically efficient to make the best use of resources that we have in the network, right? So we already have invested in billions of dollars setting up these, links, expensive fiber that we have bought. We are using these devices at here. Is it really maximizing the resources that we have? And what we observe here, what this graph is showing, is that over time it is showing that the normalized traffic rate that we have in the network, and the rate, like in general, the periods when there is this peak demand going out is relatively sparse compared to what the mean traffic rate is, right? And this ratio between peak to mean is around 2.17, right? Or you can think of around 2 times, right? So on an average, you have some traffic, and then suddenly when there is some peak going on, then you need double the capacity. So with the approach that network operators had to take was that, if we go with what MPLS is capable of, then we have to double we have to do network provisioning such that we always have double the mean capacity, right? So if the mean network usage is say 100 Tbps, then we have to build a network that can support 200 Tbps, right? And that's kind of already double the cost. And the question that network operators started questioning was that, is this something what we really need? Do we really need to provision this much? And do we really need to operate the network at half the capacity most of the time, right? For them, that was a bigger question, right? If the peak capacity is 2 times the average and peak is relatively rare, then most of the time network is actually operating at just 50% of the capacity, right? Or 50% network is only utilized most of the time. And that's a very, when you think of it from the economics perspective of building these type of massive networks, that's a huge number to take into consideration, right? So now they're thinking can we do something with MPLS to make sure that it can be more efficient, or is MPLS a bit fundamentally flawed, right? And to understand that, let's try to take an example here and try to understand the limitations of MPLS and what SDN can promise to deliver here. Okay. So we have 3 sites here, and we have 3 sites here. Okay. And we have this link, these routers, and we have this link, these routers, and we have this link, this link. So let's assume that each of these, okay, maybe let me explain that what's going on here, right? So this is site 1, 2, 3, and this is site 4, 5, and 6, okay? And we have some intermediate routers here, right? So this is a small, simple network topology that we have, where we have these end hosts here, and we have end hosts here, and we have these 4 set of routers out there. Okay, I mean, like, I'm oversimplifying. There will be a router here as well, but is like this is clear, right? And let's assume that the capacity of link for any link is 1. Okay, so I'm just putting this normalized number that every link can support traffic up to requirement of 1. Okay, and if we have the like workload where 1 is trying to send traffic to 4, 2 is trying to send something to 5, and 3 is trying to send something to 6. Okay, so if we are using MPLS, the decision is going to be something like some type of traffic engineering, which is making sure that we ensure fairness at the link level granularity, right? So the traffic, like what is the path that 1 to 4 will take? That's straightforward, right? So 1 to 4 will just go here, right? Maybe I can call something A, B, C, D. Okay. So 1 to 4, it's gonna go via A and B, and to 4, right? Between 2 to 5, it has 2 choices. It can go up, it can go down, right? And 3, it kind of like has this choice. Of course, like you can have some complicated decision that, like C can go back to 2 to A and all those things, right? But I'm just simplifying the discussion here. Okay. Now, if the routing protocols, which is the OSPF, which is just making some, like it has a local knowledge of the network, so it's going to make some greedy decisions about how it's going to, route the traffic, right? So the way OSPF works, it just looks at one link at a time under the hood, right? So when 2 is trying to send traffic through this route or this route, then it is going to share the link with 1 to 4, right? And here it's going to share link with this 3 to 6 one, right? So the decision that MPLS is going to make is that since the capacity here is 1, and we have to do a fair sharing with the other flow in place, then this will be half for this top one, and it will be half for the other one, right? Same here, okay? So now overall, what is the throughput that is delivered here with this approach? So here, like each of them are able to satisfy the demand, and each of them are able to set, 1 unit of traffic from their location, right? And can we do better in this case? Or maybe I should, okay, I should take a step back, right? So since we have made that type of decision about this greedy flow level sharing, we like 1 and 4 can only send half of their demand, right? So each of them had a demand of 1, but because they're sharing this link with 2 to 5, then they're only able to send half of the traffic, right? So when we look at 1 to 4, 1 to 4, 2 to 5, and 3 to 6, then they had a requirement of 1, 1, 1. But with this type of policy in place, it is able to satisfy 1 for this one, but for these 2, it is only able to satisfy half. Is that making sense? Okay. Can we do can we do better?
Professor?
Yeah. Yeah.
We can't see what you're drawing on the board.
Okay. Can you see it now? No?
Not
Okay.
really.
Let's,
It's blurry.
okay. Is it getting visible now?
Okay. Yeah.
Yeah.
Okay. Thank you.
All right. Yes, question.
Does 2 to 5 have a 100
Yes. So it's a sum, right? So it will send half the traffic on the top path and half the traffic on the bottom path, right? Yes.
You could do 2/3, 1/3, 2/3.
Okay, but will that be ensuring link fairness?
Yeah. Because then 1 to 4, 2 to 5, 3
but it's not link like, so okay, what let's visualize. Okay, so your suggestion is that or maybe we should just make changes here. Okay, this is clear. Is this part clear before I erase the setting here? Okay. Okay. So your suggestion is that we should send how much? 2/3 here, 2/3 here, and 1/3 here, and 1/3 here. Is that visible to you folks?
Yeah.
Okay,
Thank you.
perfect. All right. So this is not link level fairness, right? Because for this specific link between A and B, it is giving 2 times the capacity to one flow and half of that to the other flow, right? So when we just have the goal from link level fairness, then it is not, you know, like able to optimize the network requirements, right? In some sense, this is technically, if you think about it, this is actually a better policy, right? Because what it is enabling is that now with connection 1 to 4, you know, we have the satisfied, like we had the requirement of 1, and now we're able to satisfy 2/3, 2/3, 2/3, right? So this is actually better. But there is a problem that the MPLS is not able to support this type of policy because it always focuses on link level fairness. So you can, like, from the network perspective, the demand, like from this perspective, the demand that we had for the entire set of flows out there, it is fair because each of them are getting the same capacity, right? Or like, you know, their demands are satisfied to the same order. It's fair from the network perspective, but it is not fair from the link perspective. And this is actually a fundamental argument that the network operators had when they were looking into these numbers, that okay, we are trying to send traffic from here, and because once you send the traffic to the MPLS, you don't directly control how exactly the link should be shared. Like, you know, this 2/3, 1/3, MPLS will not support that, right? But when you put this type of example out there, you realize that okay, there is a better policy that we can come up with, but only if we had a centralized control over the network, right? Only if I had some type of SDN solution that was creating these, you know, tunnels and then making decision that okay, like okay, now you should send 1/3 of the traffic on this path, 1/3 of the traffic here, and then you might be able to optimize the overall, you know, performance that you're able to, or overall capacity that you can, overall demand that you can satisfy with this type of network in place, right? So this is fundamentally the argument that the network operators had back then, and that motivated them that okay, like, you know, this MPLS approach is simple, good, but it is resulting in a lot of network underutilization. It is not satisfying the demand as much as we want. And what we can do is that we can leverage this concept of software-defined networking that is out there, and like, we have to put things into context here. So these ideas were floating around the time of 2013-14, and the ideas of software-defined networking, especially in context of multi-tenant data centers, were were there from 2010, 2011, right? So first, people started thinking about software-defined networking from the multi-tenant data center perspective, which is all the optimizations within one data center, right? And then they started thinking about, can we extend these ideas in the broader network, right? And try to do something better, right? So this was the motivation for software-defined wide area networks. And this was basically, you know, like a very natural organic progression of the software-defined networking ideas. Because, you know, like something that you have to take into consideration here is that when we're trying to reason about networking in data centers, you control everything, right? So you have full control. You can support all those custom protocols and all those things in place. When we start thinking about wide area networks, you know, most of the network operators have already invested in certain type of devices, certain type of switches, right? So now, then the approach is a bit different. Then the approach is that, okay, we want to make the best use of the devices that we have already used and try to provide some type of programming abstraction that uses those devices and still does a better job, right? And you can think of SDX as one extreme, where SDX was just saying that, okay, just one switch and you can have programmability for all the participants, right? Data centers, multi-tenant data centers, they were making changes to switches on each and every physical server, right? And these are basically saying that, okay, if you change a subset of network devices, then you should be able to get the programmability, right? So the wide area network is sitting somewhere between the requirements that we have from software-defined exchanges versus the requirement that we have for the multi-tenant data centers. Okay, is this part clear? All right. So the idea of software-defined networking was very, very attractive for the network operators around this time. And what we're going to talk about, like I refer to B4 as the wide area network that Google was talking about. So B4 was termed or coined after they built a software-defined wide area network, right? And they published this work around 2013. I'm sure they were working on it for a couple of years before they did that. But that was basically a big revelation for the networking community, because until then, the multi-tenant data centers, like, there was some work going on, but people just internalized that software-defined networking is only for data centers, right? Because there you have more control. But when Google came out with the idea of B4, software-defined wide area network, then people just, got very, very serious about software-defined networking, because, this is a hundreds of billions of dollars worth of industry, right? So, like, each of those devices out there were very, very expensive. Like, companies like Cisco, Juniper, these were the vendors who were selling these network devices and selling these expensive routers that are providing connectivity between these different sites was their bread and butter, right? So now Google came out and said, like, okay, no, we're going to come up with completely radical idea where we are going to build our own switch and provide connectivity between these type of different data centers. And that was basically an eye opener for a lot of people. Like, people started thinking about software-defined networking, not just an abstract concept, which is only applicable to data centers, but something that can completely revolutionize the networking, industry altogether, right? So getting back to this specific topic, the idea of software-defined networking or software-defined wide area network was that it was enabling this centralized traffic engineering, right? So rather than relying on these, protocols, making those individual but localized but ineffective decisions, what if we have all this information, that what is the requirement of 1 to 4, what is the requirement 2 to 5, and I take that as an input to some optimizer, and then optimizer can decide that, okay, how much traffic should be sent on a tunnel between 2 to 5 via this one, or a tunnel between 1 to 4, tunnel between 1 to 6, sorry, 3 to 6. Okay, so these are the decisions that the global optimizer is going to make on behalf of all these sites that we have. So Google, as I said, like, Google's B4 was, highly visible success for software-defined networking. They actually demonstrated this by, so sometimes you write research papers and it's like, okay, this is an idea, we prototyped it, and then, once you deploy it in your network, it might work, right? So this is what SDX's approach was, that they came up with a prototype, demonstrated the value of that in simulated scenarios, and argued that, if you deploy that on your own software-defined exchange or like own exchange point, then you should get the benefits that we are promising, right? But Google's approach was a bit different for the reason that they can afford to do that. But what they did was that rather than talking about the idea first, they just built it, right? They just built this network and then published a research paper talking about how did they build it, right? And what were the challenges, what are the problems that they had to face, and how did they address those type of problems, right? So you might observe some similarities between B4 and SDX, right? So the basic premise of B4 is that it is acting as a transit provider between all these sites, right? So in principle, what B4 is trying to do is that to provide connectivity between all these different sites, it is acting as a transit provider, right? So this is a site, it is providing connectivity to all these sites as a transit provider. Now from our understanding of BGP, right? So what is a transit provider doing, right? So like if there is a transit provider and if it chooses to use BGP, right, then what will it do with each of these sites? What does a transit provider do? Think about BGP. What does any AS do in BGP? Yes, yes. First thing, they will set up a BGP session, right? So what you can have in principle is that there will be a router here, there'll be a router here, here, and they will all set up a BGP session with the B4, right? So B4 might have a router here, which will set up a BGP session, a router here, router here, router here. They will set up a BGP session, right? And now all these routers within B4 will, do their own magic to take traffic from one side to the other, right? But from the perspective of this site, all it is doing is very similar to what we had the abstraction for the SDX, right? So there is nothing that is changing from this site's perspective. It has a border router, which is like learning routes from B4 as a transit provider, and then it is forwarding the traffic to B4. Now it is B4's responsibility to take the traffic to one with a traffic engineering policy that is making the best utilization of all the network capacity it has, right? But from the participation perspective, from the change perspective, nothing really changes for all these sites. They're still using the BGP router. They're still setting up some type of peering session with the transit provider, and they don't have to do anything like magical here or like anything very radical here, right? So supporting this type of this B4 can very well not be SDN. It can very well be just a BGP set of routers, so this can be just a eBGP, external BGP session, and all these routers can have some type of internal BGP session, which is basically OSPF, right? So they just can rely on OSPF and take traffic from one location to the other, right? And this was a very fundamental design choice that Google made, that rather than coming up with some radical architecture and say like, okay, no, we're going to have all these open flow devices deployed on the network, and then all these sites have to use some unique new protocol to communicate information with each other. It just added complexity, right? So they decided that we'll keep things simple, that we know how to run a network where you have to set up a session with a BGP router and then exchange routes with each other and then send traffic to that border router, right? So these are all things that the network operators, the community was very well versed with. There's nothing unique or nothing significantly unique that is happening at each of these sites, right? And another argument that Google also had with this type of design choice was that this was kind of like a big red button that they had. This is something which is very new. They were venturing into something new that the network operators, the army of network operators, they were trained to run networks using border gateway protocol for 20 years, 25 years, right? That's the experience that they had. Software-defined networking was a new concept. There were rarely people who knew anything about software-defined networking when they were making these type of decisions, right? Maybe 10, 15 people knew a lot about software-defined networking, and then you have thousands of operators who knew how to run BGP. So what they did was that they adopted this type of model because that was a bit fail-safe. So in case software-defined networking fails, they can always revert back to standard border gateway protocols and still provide connectivity between all these different sites, even though it is not optimal in terms of utilizing all these network capacity that they have, but it might still just work fine, right? At least it will be able to handle all the mean capacity requirements that they have. So this is again a design choice that they made in this context. Now, when we try to think of B4 as a transit provider, there are some dissimilarities from the SDX perspective, right? So you can also think of this B4 and the idea of using BGP and ensuring supporting software-defined networking of flexibility while ensuring compliance with BGP. The set of challenges or set of problems are very similar in nature. The only difference I would say, or the very big difference I would say, is that SDX, in the form that we studied, was all about single site, right? So SDX was one physical switch that we were providing abstraction for. Now this is geographically distributed set of locations, right? So that's a bit of a difference between SDX and B4. But in principle, when you think about it, you can treat all these sites as the IXP participants, and you can think of this B4, one big switch that is just abstracting all the details about the physical switches that are present at different locations, but it is providing the same abstraction in some sense, right? So this site can provide the same set of policies or express the same set of policies that the IXP participants can say, like, okay, HTTP traffic has to go through site 1, and non-HTTP traffic has to go to site 4, right? So this is an SDN policy, which is similar to what we learned that SDX can also support. But now we are trying to, apply that or realize that with a geographically distributed software-defined network, right? Is this concept clear? Is this making sense? Any questions? All right, so like what we're looking at right now, it might be a bit overwhelming to see, but it's not very different from what we are seeing here, right? So in principle, the idea is of B4 is very simple, that you have these data center networks. These data center networks have massive, set of routers and servers and switches, but at the end there are these dedicated set of. So there is this router, there is this router, right? All the traffic that is, all the traffic that is internal to this data center is coming through this logical router. This logical router has a peering session with B4's router, and that's it. This is the setup that we have at a particular data center, right? The question for you, like, do you think that just one switch will be enough for one data center to connect with the B4 transit? No. Why? One will not be sufficient. Why?
The data center for a large network might be serving the whole region of the globe. So a single router would be the level.
So is that a capacity problem or some other problem? Okay. Yeah. So that's a good point, right? So there is a capacity problem, there is a security problem. There's also a port density problem, right? So when we talk about a data center, we can think of a small data center that probably you have seen at UCSB or maybe participated in some lectures on that. But we can also think of these massive data centers that we have at Facebook, Google, and Microsoft, right? So we're talking about tens of thousands of top of rack switches that are then connected to some access switch that is then eventually connected to border routers or border switches, right? So one, like this location or one switch, can it max support, supporting 30s or like few tens of ports is relatively straightforward. A lot of switches can do that, but supporting hundreds of ports is actually very tricky, right? Because you have to support this backplane in the switch that can handle that amount of traffic coming in and going out, right? So it gets very tricky. But still, there is a lot of value in having those type of switches that can support lots and lots of ports, right? But out there, when Google was building these type of networks, for the reason that you folks supported, like or argued that capacity is a limitation, the security is definitely a challenge. So we like when we say security, we want this setup to be fail-safe, right? So if some device goes down, we should still be able to provide connectivity, right? So for that reason or robustness, we want to have multiple switches. We want to given that there is this requirement of thousands of links that we want to, or thousands of ports that we want to have at these switches, we probably won't be able to support them. So we definitely need multiple of them. But at the same time, something to note here is that from Google's perspective, when they looked out into the market and then said, like, we need thousands of ports. Is there a switch that can support thousands of ports? There was none, right? Like nobody thought of building switches for thousands of ports. It's very expensive, and not everybody is going to buy that type of switch, right? So nobody was building it. Okay, if not thousands, maybe I should buy a switch. Maybe I should buy 10 switches that can support at least hundreds of ports. Are there switches that can support hundreds of ports? And then they realize that in most cases there were none. But even if there are some vendors who are building 100 port switches, they were selling it for a massive price, right? So that was not making a lot of economic decision. So what they chose to do was that, okay, let's not buy switches from these vendors. Let's just buy the merchant silicon chip that is like the switching chip that is already out there from Broadcom or some other merchant silicon providers, and build our own switch, right? So what Google did was that they combined these multiple switch chips, and then they created their own switch or version of their own switch, which actually had hundreds of ports, right? So even though one switch still with hundreds of ports, as we discussed, is not capable of providing connectivity to all these racks that we have, racks of servers that we have, but it was still better than having 1,000 switches that are providing connectivity between these sites, right? So that was also an innovation or change that Google brought in. And I think there was this was also a bit of alarming thing for all the network vendors out there who were selling these millions of dollars of network devices, when Google said okay, we can just buy off the shelf things for $5,000, $10,000, combine 10 of them together and make our own switch, right? So that was in some sense game changer from a lot of perspective, that opened up this research direction by itself, okay, what is the right way of combining all this merchant silicon chip that is out there and building your own custom switches which are suited for different type of networking requirements out there. Okay, so we know, now we agree that at each of these sites there will be multiple set of switches that are providing connectivity between these inter-site wide area network. So B4 routers that are taking the traffic are technically also present there, right? So they are in some sense co-located, right? And this is also the principle or the idea that we explored in IXPs, that there is a co-location, right? So the two border routers are sitting at the same location. They're just using the BGP border gateway protocol to exchange routes information with each other and then send the traffic, right? So the SDN policies about which flows should be sent to which tunnel is all decided at the site level router here. And then it is forwarded to the border gateway protocol. It is learning this site router is learning all the routes from B4's network, and it is forwarding the packets, right? So the design principles are very similar. What you see here is the cluster of open flow switches that are sitting at each of these sites. Because these are so many switches, right? So there are multiple control servers, NCSs, and you can think of network control servers as same as the network operating system, right? And then you have these applications that are sitting on top of these network operating system, right? And each site is making some sort of local decisions, and then there is a gateway and there is a centralized traffic engineering server that is extracting information from all these different sites about what is the requirement, what is the capacity that we have, and then making those type of traffic engineering decisions, right? So we don't have time to cover the traffic engineering optimization problem, but in principle, it's very simple. It is taking in the demand from all these sites as input. It is taking the capacity of each of those links as input, and then outputting that what is the right configuration of the network, that how many tunnels should I create and how much traffic I should be sending to each of those tunnels. Okay, is that making sense? Okay. All right, so traffic engineering, it is operating over a network topology graph. Even though there are, tens of hundreds of servers and switches out there, thousands of links out there, it just abstracts away all that detail, right? And that's very, fundamental to software-defined networking, that it is providing an abstraction that is much cleaner than network topology that it is offering to the traffic engineering server is much simplified. And then it is, using this term called flow group, basically the group of applications. So you can think of, all the applications related to Gmail services as one group, related to YouTube as another group, and so on and so forth, right? And then the tunnels, as I was referring, tunnels are basically these connections between different sites, right? So that is the abstraction that we have, that, rather than thinking about the intermediate path that it will take, you can just think of that each of those sites are just directly connected with each other, right? And that is a tunnel. Now your goal is to figure out that, okay, which tunnel should I be used to sending traffic between these pairs, right? So in this case, we have a tunnel between 2 and 5, we have a tunnel between 1 and 4, and we have a tunnel between 3 and 6. right? In fact, sorry, 2 to 5 has 2 set of tunnels in this case, right? So when 2 is making decision, it has to decide that what amount of traffic should go through tunnel 1 versus tunnel 2, right? So we have like, the tunnels, you can think of this end-to-end abstraction that we have. And between 2 and 5, it has 2 options or 2 tunnels that it has to make decisions for. Is that making sense? All right, so this brings to the end of today's lecture, where we learned that there are different types of wide area network, backend to front ends. Backends to front end is the wide area network type, which is called V2 for Google, and like the ones that is connecting the backends itself or the data centers is called B4. MPLS was the state of the art back then, and it is because it is trying to optimize or ensure fairness at the link level. It is not able to make the best use of the network resources, and it's suboptimal. And because the network requirements is just increasing, the network operators are forced to choose something that will increase the network utilization. Otherwise, the network was just sitting idle, like half the capacity was just getting wasted most of the time, right? So they had to come up with something which is more dynamic, and software-defined networking was the answer to that problem. B4 was, one of the first design of demonstrating how software-defined networking can be used beyond the data center networks, and they designed the B4 to be as or this wide area network as a transit provider, and that is an abstraction that they use. And then they, when we say transit provider, then they were relying heavily on BGP to exchange or advertise routes between different sites, and then that just simplified how the software-defined networking, all those flexible decisions are made. So whatever we learned from SDX, those principles do apply in this context, but physically the underlying physical topology was different, right? But the basic principles are more or less the same in terms of how will you express the policy, how will you forward the traffic, how will you handle the traffic within the B4. Okay, any questions so far? All right, so in the next lecture, we are going to talk about the second type of wide area network, which is the one that is connecting the front ends to the back ends.
Some of the network topology, like switches and routers, is shared between the B4 network and the B2 network. Like, let's say there's one switch between 1 and 3, and it's next 1 to 3, but also next 1 to the tops, 3 to the tops. Which abstracted network gets control of that stuff?
Yeah, that's an excellent question. And this is also a question that network operators had to think about, and they make a choice of keeping these networks completely separate and isolated from each other. So they are, physically separated network, and that's why there is no conflicts in terms of who's going to control that part of the network. But that's an expensive choice, right? So not every network can afford to make that type of choice, and there will be some networks that are operating in the middle, right? And from design perspective, it is important to understand how these really, really massive content providers are operating, but the real world is somewhere in the middle, right? So you will always find some network operators that will make a choice that you are saying, and they have to deal with these type of issues and challenges. So you have a question.
And then are the switches inside
So at the edge, they're not the normal, the one that we saw is the open flow version. But yeah, I think at the core, these are all normal routers basically, right? Because once you have translated these things into tunnels, so the dumb or the old set of routers also know how to handle traffic for the tunnels. Right? All right. I hope you had you learned something today, and in the next lecture. So next lecture, when I say next lecture, next lecture is basically the midterm allocated for the midterm. So technically you have 3 days, 2 days to finish the midterm, but that's time allocated for completing the midterm. At least you have 2 hours or 1.5 hours to finish that. So we'll not have lecture on Wednesday. Whenever we meet next is when I will talk about the B2 network out there, right? Okay, yes, question. So midterm will be released, I think I said on Wednesday, right? So on Wednesday, we'll release the midterm, and then we'll have up to Friday to finish that. And it's open book, so you take your time. 2 p.m. You want more time?
Oh, wait, I'm sorry. Did you say there is no class on Wednesday?
Yeah, there's no class on Wednesday.
Okay, thank you.
All right. All right, any other questions? Okay, all right. And I think, as I said on Slack, the assignment 2 will be released today. So you will be able to see what assignment 2 looks like soon. All right. Thank you all for coming.